Good morning, friends. We'll start API 580 and the Chapter 7 Data and Information Collection for RBI Assessment. So, the objective of this section is to provide an overview of data that may be necessary to develop an RBI plan. Data collected will provide the information needed to assess potential damage mechanisms, potential failure modes, and scenario of failure. So what you need: examples of data sources, design and construction records, inspection and maintenance records, operating and process technology records, hazard analysis and management and changes, material selection records, corrosion engineering records, and library database, cost and project engineering records. Precision of data should be constant of RBI method used. The individual and team should understand the precision of data needed for the analysis before gathering it. It may be advantageous to combine risk analysis data gathering in other risk hazard analysis data gathering, as much of the data may be same. An RBI study may use a qualitative, semi-qualitative, and a quantitative approach. A fundamental difference among these approaches is the amount of detail of input, calculations, and output. Any deviations from prescribed standard procedures should be documented. Data needs for qualitative RBI. It is important to establish a set of rules for assure consistency in categorization of classification. Generally, the qualitative analysis using broad ranges require a higher level of judgment, skill, and understanding from the user than more quantitative approach. Data needs for quantitative RBI. Quantitative RBI use logic models depicting combination of events that could result in service accidents and physical models depicting the progression of accidents and transportation of hazard material to environment. The models are evaluated probabilistically to provide both qualitative and quantitative insight about the level of risk and identify design, site, or operational characteristics that are the most important to risk. Hence, more detailed information and data are needed for a fully quantitative RBI in order to provide input for the models. Data needs for semi-quantitative RBI. The semi-quantitative analysis typically requires the same type of data as quantitative analysis, but generally not as detailed. Data quality has direct relation to the relative accuracy of RBI analysis. Quality of input data is equally important no matter what approach RBI is selected. The data inputs and assumptions shall be validated by qualified personnel such as process engineer, operator to review operating parameters used. Outdated drawings and documentation errors within the inspection planning, execution, documentation, clerical and data transcription errors, the quality errors, measurement equipment accuracy. For example, if baseline inspections were not performed and documented, nominal thickness may be used for the original thickness. As mentioned previously, the data validation has been priority of RBI. The time required to do it get included. Data validation step is necessary for quality of any inspection program, not just for RBI. Unfortunately, when the data validation step has not been priority before RBI, the time required to do it gets included with the time and resources necessary to do a good job on RBI, leaving the wrong impression with some managers believing that RBI is more time consuming and expensive than it should be. Codes and standards, national and international. The selection and types of codes and standards used by facility can have significant impact on RBI results. Sources and site-specific data information. It is important to stress that the precision of data should match the complexity of RBI method used. The PNID is process flow diagram, material selection diagram, MSD, MSDS, etc., piping isometric drawings, engineering specification sets, material of construction records, construction quality assurance, quality control, QAQC records, codes and standards. So use protective instrumentation system, leak detection and monitoring system, isolation system, inventory records, image, emergency depressurizing relief systems, safety systems, fireproofing and firefighting systems, layout. Inspection records, schedules and frequency, amount of types of pre-inspection, repairs or alteration, positive material identification, PMI records, inspection results. Process data, fluid composition analysis, including containments of trash components, distributed control system data, operating procedures, startup and shutdown procedures, emergency procedures, operation logs, process records, PSM, PSI, PHA, RECM, FMEA and QRA data reports, MOC records, offsite data and information if consequences may affect on offsite areas. Failure data, generic failure frequency data, industry or in-house industry specific failure data, plant and equipment specific failure data, reliability and condition monitoring records, leak data, site condition, climate, weather records, seismic activity records, equipment replacement cost, project cost report, industry database, PSM studies, PHA studies, QRA studies, other site specific risk and hazard studies, incident investigation. Then comes damage mechanism and failure modes. Damage mechanism includes corrosion, cracking, mechanical and metallurgical damage. Understanding damage mechanism is important for the following: analysis of POF, probability of failure, selection of appropriate inspection intervals, due dates, location, techniques, decision-making ability, modification of the process material selection, monitoring etc. that can eliminate or reduce the probability of a specific damage mechanism. Failure modes identify how the damage component will fail. Analysis of COF, run-off repair decision making, select the consequences of failure, selection of repair techniques, non-repair decision making. Identification of damage mechanisms, identification of credible damage mechanisms or failure modes for equipment included risk analysis is essential to the quality and effectiveness of the risk analysis. The RBI teams will consult with corrosion specialists to define the equipment damage mechanisms, damage modes, optional and potential failure modes. A sequential approach is as follows: equipment design, pressure, temperature and materials of construction and current conditions shall be considered. All process conditions, startup, shutdown, idle, anticipated, abnormal, normal, as well as planned process changes shall be considered. Identifying trace constituents, PPM, in addition to primary constituents in the process can be very important, as trace constituents can have significant effect on the damage mechanism. Deterioration, degradation is sometimes used as a synonym for damage. The term aging mechanism is used to some industries to identify subset of mechanisms that depend upon long-term exposure at specific temperature or cyclic stresses. So corrosion under insulation may precipitate a damage mode of either generalized corrosion or localized corrosion. Generalized corrosion could result in large burst, while localized corrosion might have more likely the result in a pinhole type leak. In damage mechanisms, process specialists can provide useful input such as spectrum of process conditions, injection points, etc. Failure modes. Once a credible damage mechanism has been identified, the associated failure mode should be also be identified, and the failure mode will depend on the type of cracking, the geometric orientation of cracking, the properties of material of construction, the component thickness, the temperature, and the stress level. Examples of failure modes include the following: pinhole leak, small to moderate leak, large leak, ductile rupture, brittle fracture. Ductile rupture, brittle fracture. Okay. Accumulated damage, an evaluation of, okay, in some cases damage by one mechanism may progress to a point at which different mechanism takes over and begins to dominate the rate of damage. An evaluation of damage mechanism and failure modes should include the cumulative effect of each mechanism and or mode. So tabulating results, credible damage mechanisms list. Example, external corrosion, localized thinning, generalized thinning. Localized thinning, failure mode pinhole leak, failure mode small leak, general thinning, pinhole leak, small leak, large leak, rupture. Okay, we'll stop here.